I now take up Taylor's formula for e raised to the power x. Here, if f of x is equal to, let's say f of x is equal to e raised to the power x, I know that the first derivative is e raised to the power x, the second derivative is e raised to the power x, the third one is also e raised to the power x, and so on and so forth. That means I can say that all the derivatives of f are equal to e raised to the power x. That means the fourth derivative, the fifth derivative, and in fact I can say the kth derivative, that is also equal to e raised to the power x. And in each of these derivatives, if we put x as 0, the value will turn out to be 1. So f prime 0 is going to be 1, because f prime 0 is e raised to the power 0, which is 1. F double prime 0 is also 1. F triple prime 0 is also 1. Even the value of the fourth derivative at x is equal to 0 is 1, and so on and so forth. That means I can now say that the kth derivative of f at x is equal to 0 is 1. And I can then write f this 0 is equal to 1 for k is equal to 1, 2, 3 till n. So the value of the first derivative at x is equal to 0 is 1. The value of the second derivative goes on till the value of the nth derivative. Now I can use the Taylor's formula, and if let's just get to what the Taylor's formula was. So in the case of the Taylor's formula, I can write f of x is equal to f of 0 plus 1 upon 1 factorial f prime 0 x plus 1 upon 2 factorial f double prime 0 x squared plus 1 upon n factorial f of this 0 x raised to the power n plus 1 upon n plus 1 factorial f of this c x raised to the power n plus 1. And here I can write this is for some number c between 0 and x. Given this, we can write the Taylor's formula for e raised to the power x, and that means that will give us e raised to the power x, that is my f of x, f of 0. f of 0 is e raised to the power 0, which is 1, plus 1 upon 1 factorial f prime 0 multiplied by x. I know in this case that f prime 0, f double prime 0, even this, all these, as in the values of all these, the values are equal to 1. That means I can write 1 plus, I can write x by 1 factorial plus x squared by 2 factorial, and it goes on till x raised to the power n by n factorial. And then I can write, even in this case, I can write x raised to the power n plus 1 divided by n plus 1 factorial and here I have the n plus 1th derivative evaluated at c. So this is going to be e raised to the power c. Again, we have to keep this in mind that in this case I should write for some number c between 0 and x. Given this Taylor's formula, so this is something we have to keep in mind. Given this, if I am asked about the estimate of e raised to the power 0.1, if I want to note this, keeping in mind that n is equal to 3. The point to note is I would like to know the estimate of e raised to the power 0.1. What is this? Given that n is equal to 3, and again I can use the Taylor's formula, keeping in mind the fact that n is equal to 3. So I can go for e raised to the power 0.1 is equal to, it's 1 plus, so here x is equal to 0.1. So it's 1 plus 0.1 by 1 factorial plus 0.1 squared by 2 factorial plus 0.1 cubed by 3 factorial plus 0.1 raised to the power 4 by 4 factorial, and then I should write e raised to the power c. I should then write for some c between 0 and x. So x here is 0.1, so I should write for some c between 0 and 0.1. Now c is between 0 and 0.1. That means I can write for some c belonging to this interval. I can now write what this is. E raised to the power 0.1 is equal to 1 plus, I can now write 1 by 10 plus 1 by, this should be 1 by 200, then this should be, it's 3 factorial I know is 6, and it's 0.1 cubed. That means it should be 1 by 6000, and here it should be, it's 0.1 raised to the power 4. 4 factorial I know is 24. So this, and let me just write 0.1 raised to the power 4 divided by 24 e raised to the power c. Again, for some c in this interval, and please keep this in mind that c belongs to 0, 0.1, this interval, this open interval. Now if that is the case, c is lying between 0 and 0.1. Let's think of this expression here. And in this case, I know that c is lying between 0 and 0.1. That means c is less than 0.1. And that means e raised to the power c will be less than e raised to the power 0.1. So that means I can now actually calculate from the calculator what is e raised to the power 0.1 here, and this will give me this, e raised to the power 0.1 this turns out to be 1.1, which is certainly less than 1.2. The reason I have taken up 1.2 here is because we have 24 in the denominator. So that means I can write that this is definitely less than 1.2. What does that mean? That means I can say that this expression, which is 0.1 raised to the power 4 by 24 multiplied by e raised to the power c, this is less than, and obviously I know that this is greater than 0, this is less than 0.1 raised to the power 4 divided by 24, and e raised to the power c I know is less than 1.2, because e raised to the power c is less than e raised to the power 0.1, which is less than 1.2. That means I can now write this. So this can then be written as 0 less than 0.1 raised to the power 4 by 24 e raised to the power c, which is less than, now I can write that as 1 by 24 it should be, I think, yes, these many zeros and then 1.2. So I can calculate this. So it will turn out to be 0.1 raised to the power 4 by 24 e raised to the power c. This turns out to be, so this is 1.2 divided by 240,000, which will turn out to be 0.0000005. So that means if I drop this remainder, in fact I should just remind you that this is nothing but my remainder. If I drop this remainder, the error, as in the remainder, if I drop this remainder, this will be the error, and the error is going to be this 0.1 raised to the power 4 divided by 24 multiplied by e raised to the power c. Now this error is going to be less than this expression. It's going to be less than 0.000005. And that means if I go by this approximation, if I go by the third order Taylor polynomial approximation, wherein I only consider this, the error is going to be less than this expression 0.000005. So error is going to be less than this, and that means I can actually go for this approximation e raised to the power 0.1. I can now go for 1 plus 1 by 10 plus 1 by 200 plus 1 by 6,000. If we go by this approximation, the error that results is less than this expression. And that means if we calculate this, we will get e raised to the power 0.1 approximately equal to 1 plus 0.1 plus 0.005 plus 0.00017, and that means e raised to the power 0.1 will be approximately equal to 1.10517. Now this is accurate to 5 decimal places, and the error that results when we estimate e raised to the power 0.1 by this expression, the error that results is less than this. It is less than 0.000005.